So today we're going to talking about whether XPS is the right technique for your analytical needs, the question that you're trying to study. So first, what is XPS? XPS is a spectroscopic technique that provides accurate quantitative, elemental, and chemical composition from the top 5 to 30 nanometers of the surface. The key to the success of the XPS technique is quantification and chemical sensitivity. It's also non-destructive, fast, and easily accessible. As we will look at the process of XPS, we have a sample that is being bombarded by the X-rays, and these X-rays eject photoelectrons, hence the name X-ray photoelectron. And based on kinetic energy of the electron that is being analyzed in the analyzer, we can determine what is the binding energy of the electron, and that is providing us information on what is the element present and what is its chemical state. So why XPS is such a popular technique? It's most widely used technique as it can be applied to a really large range of materials, and it provides, like I mentioned before, quantitative and chemical state information. There's a variety of applications and industries that use XPS as the routine standard technique. Important in both industrial and research development. Surface composition plays, of course, a critical role in performance of functional materials, of polymers, photovoltaic, batteries, semiconductor devices, and therefore it's being used widely by these industries. Depending on the instrument, you can analyze a variety of different sizes on the sample from a large area to as small as 5 microns on 5 XPS instruments. So what sort of application are popular, or you can see, and it's by no means it's a complete list. Of course, the basic analysis is elemental and chemical state, a characterization of variety of materials from polymers to metals, catalysts, nanomaterials, etc. In addition to that, XPS is powerful to extract composition and calculate thickness of thin films. Corrosion studies of metals and alloys is another application. Failure analysis, correlating your failure reasons with the performance, surface contamination, and variety of different interface studies. If you search for XPS in any industry, this is just example for semiconductor technology, the number of publications has risen dramatically in recent years. And the main reason for that is ease of use, accessibility. The instruments become more accessible to users. And at the same time, the power of quantifications and chemical sensitivity. There is no material research paper that is published right now in any of the journals for any type of materials without XPS being one of the analytical techniques in the portfolio. So first, before proceeding, I would like to start a quick poll. If you are using XPS, I would like to launch it. The question that I would like you to answer is, when you use XPS in your research or development, you have a particular analytical problem. How often XPS is successful? Every single time, most of the time, 50-50, maybe. I hope you will not see any questions in the it fails every time category. So majority of you have answered. Thank you so much. So I'm going to end the poll. And these are the results. I'm sharing the results with you. So we have 11% every single time, 80% most of the time, and 59% of the time. So the photoelectric process is behind the XPS as a method. So again, we're using incident X-ray to eject the electrons. We know what is the kinetic energy of our X-ray source. If the energy is higher than the binding energy of the electron on the orbital, this electron will be ejected. And this electron will have kinetic energy. This kinetic energy is what we're measuring. We are measuring number of electrons at specific kinetic energy as they come out from the sample. And we can then, based on this relationship of photoelectric effect, we know what is our X-ray source energy, we're measuring kinetic energy, and we can calculate binding energy. And binding energy is a function of both chemical environment balance state, coordination, and other properties, intermolecular interaction. This is, again, what makes XPS such a widely utilized technique. What are the factors affecting success of XPS instrument? By no means it covers all of the factors. There is not enough time to cover all of them in one webinar. But these are some of them that I would like to address. First is the sample state, then the relationship between the surface or the part of the material that defines the function and information depths, detection limit, how accurate your quantification, what area of the sample you really need to analyze, how to handle overlapping between different peaks. One of the most probably challenging is chemical shift, and also some of the effects of parameters used for thickness calculations. This poll will be a little bit longer. I would like to for you to look at this question. So there's 10 parts of XPS experiments, and I would like to choose top three steps in your process of creating information out of XPS experiment. Well, thank you so much for your responses. So let's look at the results. So you can see that the biggest challenge, like I mentioned before, is curve fitting. The second is chart referencing. We will talk a little bit about curve fitting. Chart referencing is definitely another probably whole topic for the separate webinar. Choosing correct instrumental parameters and chemical state identification are two other top choices, and accurate quantification. So this webinar will address some of these factors. So let's start with just sample state. Whether you can even put your sample into your XPS system. Of course, it comes with UHV requirements and size limitations. You cannot put as large sample as you want into your XPS instrument. So this is quite obvious. In terms of sample outgassing rates. So for UHV applications, the recommended outgassing rates are between 10 to the minus 10 and 10 to the minus 12 liter per second. There are some plastic rubbers and adhesives that with high outgassing rates. Some metals may undergo oxidation or release contaminants. There are reference parameters that you can reference books that you can find online with outgassing data. So this is one of the older publications that I found just by using search, the PDF file that has some of the outgassing rates. Sometimes we may introduce unclean particles or contaminations onto the sample. We get samples all the time that was shipped in the container that contributes something that was not a part of the sample before it left the customer hands. So how the sample was delivered, stored, or handled can affect the information that you are receiving out of the experiment. So always, of course, ensuring sample cleanliness is important. If you have a sample that you're not sure that is in borderline, for example, of your gassing rates, you can always load it into interchamber and see how the pressure, you know your instruments, you know how fast does it take for your samples to pump down. And that is a good test to do. But of course, definitely check the data first. The second, I would like to talk about the relationship between what is the actual interest from which part of the depths you would like to get the signal versus the information depths that XPS gives the signal from. So X-rays penetrate microns into the sample. Well, electrons travel throughout the material, and only electrons from the first few layers escape without losing the energy. Some of the electrons from deeper may still escape and contribute to the background of the spectrum, while the even more deep electrons will not be able to escape. That's what provides us with surface sensitivity. So when we define that information depths, this is the equation that defines it. So we can see that it's 3 times this parameter lambda, which is we call an elastic mean free path, times sinus theta. So theta is just an emission angle relative to the surface. So at 90 degrees takeoff angle, we can have the largest information depths. An elastic mean free path is a parameter that defines what is the distance an electron can travel between collisions and lose the energy completely. And there are tons and tons of publications that you can find for defining empirically and experimentally and theoretically an elastic mean free path. Universal curve is something that many of you may have seen before. This universal curve, unfortunately, does not take into account material properties. Like I mentioned before, there are many detailed experimental measurements and calculations that you can find. If you have a material that you work with, you may be able to find a good publication, a good reference. For example, the organic material study has, for a certain range of energies, a suggestion what is the dependence between an elastic mean free path and kinetic energy. There are many seminal papers published by Martin Sia from PNL and his collaborators on database and equations that customers can use, scientists can use to calculate electronic mean free path. And when I will be talking about thickness calculations, I will show some of these equations. Something else to remember, when we talk about information depths, with let's say we have an elastic mean free path that we have found in the database calculated 3 nanometers. So it tells us then our information depth is 3 times that, which is 10 nanometers. But it's not as simple. Because of exponential dependence of the probability of electron escaping with depths, 63%, 1 sigma of the signal comes from 3 nanometers. 85% will come from 6 nanometers, and 95% will come from 9 nanometers. And that becomes important when you're looking at physical dimensions of your material within that overall XPS sampling depths. So this is something that sometimes is being overlooked. So if you think of core shell structures as example of how the physical dimension of the sample is related to the information depths, there are a variety of different structures that can be created. And of course, there are a variety of different dimensions of the core shell nanoparticles that can be created. So here's an example of larger ones, but just for demonstration purposes we have here a particle with gold core and cerium oxide shell. If you look at the gold 4F and cerium 3D transition that you would analyze to get, let's say, the ratio between those two to confirm your composition, they come from information depth that is quite similar. So it's quite easy to interpret these results. Here's another example. Quantum dots based core shell nanoparticles have often cadmium selenium core and zinc selenium core and cadmium selenium shell. Information depths in this case is quite different. Selenium that present in both core and shell comes from as large as 9 nanometer sampling depths. Cadmium comes from 5, while zinc from 3. So if you have a nanoparticle that is of similar dimension, let's say between 2 and 10, the interpretation of the composition becomes really challenging without taking into account where the signal originates from. So that's something that you need to be really aware of. You need to be aware of different elements may have different sampling depths. Don't forget exponential contribution. Don't forget that majority of the signal comes from 1 lambda. And take into account physical dimensions of the particles with respect to the order of the sampling depths. Now let's talk about detection limits. If you have a sample with certain contamination on doping, a customer brought you a sample, they would like to confirm that you can detect that contamination or dopant, whether you can do it with XPS. Usually when you report a big number, what is the XPS detection limit? It's usually put between 0.1 and 1%. However, we have lots of data now that helps us understand and plan the experiment. Alex Shard from PNL published a really important paper with detection limits for more than 6,000 binary systems for using both aluminum and magnesium X-ray source. So here's an example of the plot that is included in that paper. You have here trace element and the matrix element. So you can see how different these detection limits can be. Detection limit in light element in the light matrix can be as small as 0.003, while when you have matrices of the higher Z elements and trace element as well, it can be as large as 10 or not even detected at all. So this can be first step of guiding your expectation for your hypothesis for your experimental design. So reminder that detection limit is not just 0.1 to 1, like we often see. It is element and matrix specific. And if you don't see the element, it doesn't mean that it's not there. There are other analytical techniques with better detection limits that should be used to confirm the absence of the elements or tokens. Quantification. We saw that accuracy quantification was one of the highly critical responses in the poll. So what do we have as a sample? Ideal surface. Everybody wants to work with ideal surfaces. Contaminations cannot be eliminated. There are definitely tools with vacuum transfer vessels, glove box attachment that really allows us to work with ideal surfaces. You can deposit it in film as a part of your design. You can have a buried layer that you're interested in analyzing. You can create microstructures as a part of your design, or the sample can be inhomogeneous. The surfaces can be rough, or they can be particles. But when we look at the quantification of assumption of the formula, what has been assumed is ideal surface. So the formula that relates the intensity of the peak that we extract in XPS spectrum and atomic density of that element assumes homogeneous sample. The parameters that go into that calculation, many of them are instrumental: detection, detector efficiency, X-ray flux, analysis area, analyzer transmission. Some of them are specific to the material: elastic mean-free path, cross-section of the electron, or ionization probability, how many electrons you will produce per photon, that are tabulated data. So this relationship is quite well understood, but it assumes homogeneous sample. We don't usually report XPS composition in atomic densities. Usually we work with sensitivity factors. And sensitivity factors combine all of these parameters into the factor that is derived based on either reference pure elements or compounds, so basically based on empirical data. So when you are getting inaccurate quantification, there is definitely something to consider. Is your sample homogeneous? That's the first question that you need to ask. Because we're working with fractional numbers, we always we assume that the total composition of all of the elements that we report in the paper is 100%. So when you read a paper and you see a comparison, we always need to be aware of whether the survey spectrum has been shown, whether all of the elements has been included into quantification. Because when you remove one of the elements from your quantification, the absolute or relative rather atomic concentration will be different. So really, you have to be really careful comparing between your samples consistently. And ratios are really useful way to compare whether you have some sort of treatment of your material or a series of samples that you're working with. There was really important paper that discusses quantification accuracy in terms of the way that we even approach the background selection. So please refer to this paper that was published by Dick Brundle and Vince Christ in 2020, when they looked at very simple lithium fluoride, 1s electrons, and they were looking into whether the cross-section or sensitivity factors include all of the intensity that is coming from the photo ionization process. And they mentioned that there are losses, of course, that we all know, the shake-ups and satellites, and the percent of losses depends on the chemical state of the atom. And therefore, you have to be aware how the sensitivity factors were derived and how you also process the data for quantification. So here's just an example of looking at silicon 2s and silicon 2p for 3 different compounds, metal and nitride and oxide. and aluminum 2s and aluminum 2p for metal and oxide, you can see immediately that metal has almost half of the signal is being lost due to shake-up and other phenomena that happen when electron is traveling through the material. For compounds, it's much smaller. It's an order of 30%. So this is something that you need to be aware when you are doing quantification, the way that you define your regions for quantification. Spatial specificity. So I would like to ask you another question. So this is the question related to small area analysis. How often do you use small area analysis? Regularly, occasionally, very rarely, or never? Well, thank you for responses. I think majority of you responded. So let me share the results with you. So you can see that majority of the customers do use small area analysis. And it's very good to see because it's very important for us to understand whether our samples are heterogeneous or homogeneous. So let me show us another paper that has been published by Don Bayer and Mark Engelhardt from PNNL in 2000. It is focusing on selectivity. How do we even determine whether we're getting the signal from the right area on the sample in small area analysis experiment? But it starts with overall approach to most of the XPS. Analysts, of course, would like to increase the throughput, to increase the count rate, and to improve the signal-to-noise ratio. They usually do large area spectroscopy, and they assume that the composition that they get is representative of the average information. But there are many phenomena that can contribute to differences in signal intensities over large areas. And therefore, you have to be really careful when you assume that it's representative of your surface composition. So here's an example of just blank film on glass. I realized 3 different areas, large area, quantified them. So we have major elements, carbon, oxygen, and then smaller compositions plotted in the blue. So you can see that in this case, we have standard deviation on the order of less than 5%. So we can derive that it's the area from area is homogeneous. So large area spectroscopy is an adequate way to analyze this sample. Here's another example. We also have glass and we have composition. So we have carbon and oxygen and some different properties, elements in the film. So we can see that here now we have lot heterogeneity. The standard deviation is an order of as large as 70%. So we now realize that probably large area spectra is not giving us the full picture. So when we now go to small area analysis, we can understand what's happening in more details. So here's an example of looking at that film using our secondary electron image that is induced by X-ray microprobe. So we can see immediately that we have bright areas and we have darker areas. And then we can select appropriate size for the small area analysis, which is usually we assume 3 times smaller than the feature that we are interested in. And we can see that indeed, there is no expected silicon and lead in the darker areas. So without that information, we would probably derive different conclusions. And it's always useful to use other analytical techniques, complementary microscopic techniques, to confirm what you know about the sample's heterogeneity. Now let's talk about chemical shift identification. That curve fit, it was the #1 challenge. So we are really taking advantage of chemical state sensitivity in XPS. Whenever electron is participating in chemical bonding, valence electron, due to electrostatic effect, it propagates and affects all of the other core levels. And we have databases that allows us to identify what is the chemical shift due to what chemical environment it can be. Generally, when we withdraw electrons from the valence electron, binding energy increases. But with very general rules, there are exceptions. And that's why we have databases that help us understand it. The biggest shift is usually observed when you have nearest neighbors with the largest electronegativity difference. So carbon bound into fluorine, 2 or 3 fluorines can have as large chemical shift as 6 eV. The features of the spectra contribute to, of course, there are multiple features that contribute to the overall spectra. So it's not just the chemical shift that result in the shape that we see right here. But what we would like to extract is that chemical state information. We can have spin orbit splitting. We can have shakeups. We can have plasma lines. Of course, background has to be treated adequately in order for us to correctly define the area that only comes from the photoelectrons belonging to that transition. There may be overlapping other peaks, elements, or jet transitions. So the goal of the curve fit is to identify and separate all of these contributions for accurate quantitative analysis of different types of chemical states. The prerequisite, so here's some common mistakes that we see in the literature. Here's an example when orbit splitting is being ignored. Only one part of this calcium 2p spectrum is being fitted with, which is incorrectly assumes they losing all this area in counts in intensity where background is selected incorrectly. If the spectra is really of poor quality, you're not going to extract useful, accurate information. You cannot overinterpret data. In this case, is an example of overinterpreting data. Here's an example of incorrect background. We are losing some intensity by choosing incorrectly endpoints. Now, probably the most common one is varying widths of the peaks. Here's an example for curve fitting nitrogen 1s, where you assume the chemistry that you begin with, and then you do some treatments, and then you derive conclusions, but you derive conclusions by having your peaks that are almost 3 times different in widths. So we have a peak at exactly the same energy at unparalyzed hair sample, and for some reason at 900 degrees, it's now 3 times more narrow. There is no physical processes that would allow us to explain this phenomena. So this is another quite common mistake. The prerequisites for any analysis of XPS data, but specifically if you would like to do chemical shift analysis, is of course your instrument has to be calibrated. It affects the quality of the data. Using correct background subtraction scheme, it affects how the areas under the peak are calculated and therefore your quantification results. Effective charge neutralization system, that will affect the binding energy accuracy and therefore your identification. And charge correction. This is something that was number 2 most challenging, and I'm not going to address this here, but I'm going to leave some of the references at the end of my talk. So all of this assumes that we've taken care of that before we actually trying to curve fit the spectrum. So this is how the good appropriate publication with appropriate curve fitted data should look like. You always need to report how the charge correction was done. You always should include the background that you used. You need to show original data. You need to include the sum of all of the physical components and residuals that results. You have to not forget all of the physical processes that happen, shakeups, satellites, speed orbit splitting. The goal is not to mathematically feed the spectrum. We need to really derive based on chemical and physical processes. You need to add reasonable number of components and use similar widths of peaks, as all of this information is really now well accessible in databases. And something that we should remember, that sophisticated analysis does not fix low quality data. And all of the parameters that you use in curve fit, binding energies, full width half maximum, the shape, Gaussian-Lorentzian shape that you used in the curve fit have to be reported in your paper. So now I'd like to talk about peak overlap of main elements of interest. This is related to curve fitting, but it gets even more complicated. For example, quite common example is gallium nitride. So gallium nitride has a problem because we have gallium signal that overlaps with nitrogen 1s, and there is no other nitrogen peak that we can use for quantification. So as you can see in this paper, there are 3 peaks that have been used to curve fit the nitrogen 1s region, and they come from the gallium signal. So how do you do that? You need to do references. You need to know what intensity of this gallium Auger transition to include that really comes from the gallium, and that you're not removing some of the signal that belongs with nitrogen 1s. Very typical example of molybdenum disulfide. So we have here sulfur 2s that it's actually quite easy to handle overlap. They're much worse than we of course that we see, but this is still something that has to be included and reported for accurate quantification results. This is another example of antimony oxide. Here we have, without using the doublet spin orbit doublet splitting, we would not be able to separate out oxygen, because we see here that 3-half transition does not have any contribution from the oxygen. And we know what is the separation between orbitals splitting 5-half and 3-half. We know based on quantum number what is the relationship in intensity between 5-half and 3-half. So we can constrain our curve fit of this part of the spectrum where overlap happens and extract the area that belongs to oxygen accurately. So when you have overlaps, it relies on running references and really carefully constraining your curve fit so that you can really take into account those overlapping peaks. And sometimes it's come to a point where it's not possible to constrain and it's not possible to quantify. And then by understanding in general how much of the other peak may contribute, you may report the values and report that it may be overestimated because you have other contributions that you cannot exclude. The last factor that I'd like to address is the parameters that we use for thickness calculations. So in angular resolved experiment, as a powerful experiment that allows us to calculate thickness of thin films. When we change angle in takeoff experiment, remember the information depth equation. We have our information depth that is related to inelastic mean-free path, but it also is related to takeoff angle. So when we tilt our sample, the effective travel depth of the electron stays the same, but the information depth from which we sample decreases. So here's an example of silicon 2p with native oxide layer. And we can see that for the larger takeoff angle, which is this orange curve, we have much higher contribution from metal substrate, while the red one is 20 takeoff angle, which is surface, looking more at the surface part of the sample. We have equal contribution of metal and oxide. So it's non-destructive method that allows us to do depth profile within overall XPS sampling depths. And accurate structure can be calculated up to 2 lambda thicknesses, sometimes even maybe larger, but then the uncertainty becomes contributes to your thickness calculations. The variety of models that extract thicknesses from your angle-dependent data. One of them is straight line approximation. So it looks at what is my intensity of electrons that comes from the substrate, as it travels through the overlayer at different takeoff angles. So it looks, this is the intensity of the substrate. This is my takeoff angle, and it is related to thickness. So this is what we model in. We model in thickness. But something that I would like to bring your attention to is actually this, again, lambda. The accuracy of the thickness will depend on the inelastic mean-free path that you use to calculate, to describe the properties of the electrons that as it travels through the overlayer on your sample. In the paper that I showed before by Margensia, there are four parameters, four equations that are being suggested. The first one is probably the most common. Most of the databases are using TPP2M. So we can see that it's an empirical equation, and some of the parameters that included in these calculations: molecular weight of your material, density of your material, number of valence electrons, and we also have energy gap that is included in these calculations. So you can see that this method is probably the best when you know your material well, and you know the density, etc. All of these parameters that you can include in an elastic mean free path formula. Here's an example where it's a simpler formula that is suggested in the same paper. We can see that it depends mainly on atomic number and kinetic energy. And then this parameter, we have, again, molecular weight and density. So again, it's a formula that is suggested for another formula for calculation of an elastic mean free path. Two other formulas are actually trying to take into account scattering effects. As electrons are traveling through the material, they scatter. And this is what we call effective attenuation lengths. So you can see another empirical formula with numbers and that depend on the material properties. So these all three equations are really sensitive to material properties. So if you have those parameters, then you should use them. If you have a material that you work on in the lab and you don't have the property, that density, etc., then there is a very simple equation that is dependent only on kinetic energy and atomic number. What I would like you to show you is how different these values are for the same material. This is just for cadmium 3D transition. Look at the difference between the attenuation effective inelastic mean free path and effective attenuation length. So depending on the thickness, on the value of this inelastic mean free path that you use, your thickness will be different. So the thickness that you extract from angular dependent experiment is as good as your assumption behind all of these formulas and the model used. And something that you should definitely avoid when you in your models is mixing methods for inelastic mean free path. If you have multi-layered structure and you know properties of one layer but no properties of another, you should not mix TPP2M, for example, with scattering formula of equation 14 in this paper. So we'd like to point you all to this topical collection. It's the first issue of the collection, and right now there's second that being worked. So American Vacuum Society has the Journal of Vacuum Science and Technology, and Don Bayer has led this effort for the last 2 or 3 years. And there was a first issue that came out, a collection of papers addressing reproducibility challenges with focus on XPS. And this is something that addresses many of the topics that I described today, charge correction, etc. And I'll show you all of the papers that are published as a table. And it discusses high-level challenges, setup of calibration of the instrument, sample consistency, whether it's correctly handled, stored, and mounted. It may be damaged. Analyst issue, whether it's a limited understanding of the instrument and technique requirements and decisions that are being made because it impacts the quality of the data. And we have seen a really crisis. This whole initiative has started from the recognizing that we are seeing incomplete records, incomplete reports on the experimental conditions, and inadequate processing of XPS data in literature, and so often in very highly ranked journals. So how do you plan the experiment based on kind of that? Of course, you need to understand what is the analysis objective and what information is thought. Do you need elemental composition or chemical composition? Is it a contaminant analysis? What are the expectations for your concentration level? Will the texture limit of that transition, of that element be within what you're trying to analyze? Is your sample heterogeneous? Is there a specific part of the sample that you would like to analyze? When you work with customers or work yourself, any other information for analytical techniques is really useful for planning your experiment. Some sample-specific things to know. Is sample air sensitive, so you really need to use some special tools? What is the vacuum compatibility? What is the sample conductivity, whether it will define whether you need to use neutralization? Is sample maybe susceptible to X-ray damage? Then the time of analysis becomes an issue. How the sample was handled, and whether there is some specific synthesis related, whether there are natural defects or patterns that you need to know about. Based on that information, you can decide what sort of spectra you would like to acquire. Can you just look at surface spectrum to detect your elements and to provide atomic concentration, or you need to do chemical analysis, and whether the chemical shift will be large enough within the uncertainty of our energy resolution of the instrument. Whether there is overlap between the peaks, whether you need then to plan to acquire other transition to help you and to acquire references to help with curve fit. Are there any other types of data that may be needed, angle resolved to the depth profiling, imaging, or other special approaches to really be successful in working with the customer? And of course, you need to really think of appropriate statistic quality of the data and replication of measurements, so you can really report the uncertainty of your measurement in a paper or to your customer. And I have it as the last, but it's usually the first, to appropriately set up, verify performance, and check calibration status of the instrument. This is without that nothing else matters. And references, if you have references, they always help. It's better to invest time to running references and analyzing your actual samples than realizing later that without references, you're not able to answer the question. So this is a table for this first topical collection. So we can see that it has several sections. It has section on planning the experiment, setting up and collecting your data. And this is what talks about the charging effects. There is a whole section on peak identification, peak fitting, and quantitative analysis. And it talks about quantitative accuracy, backgrounds, curve fitting. Then it talks a lot about the attenuation lengths and how do we actually interpret the depths information, and the data reporting, how we report the data. So if you are working on yourself on XPS, this is really useful handbook, which you refer to in your experiment for really to help you out to be successful in XPS experience.